When it comes to the music we love to listen to, it is simply mechanical resonance. The standing waves that get created on or in musical instruments correspond to resonant frequencies. When you pluck a string, for example, lots of waves of lots of frequencies get created that travel down the string, but most of them quickly die out. Only the resonant frequencies that correspond to standing waves persist, okay, and correspond to the notes that we end up hearing. True that musical sounds don't seem to have a lot in common with the vibrations that cause buildings to crumble and bridges to collapse, but everything we learned about resonance in our last lecture applies here, okay, in the case of standing waves formed within instruments. The resonant frequencies get reinforced, causing large amplitude vibrations of a medium that end up being the notes that we hear and call music. In this video, we'll look specifically at standing waves formed on stringed instruments like guitars, violins, and pianos, as well as standing waves formed in wind instruments like flutes, trumpets, and oboes. Oh, and by the way, you may also learn how roosters can end up playing the piano. So we'll start today's lesson by talking about standing waves in stringed instruments, and from there we will move to the standing waves that get formed in wind instruments. So let's just start by taking a look at some common examples of stringed instruments. So obviously the guitar represents a stringed instrument, okay, a set of strings that have the same length and fixed at both ends. Okay, the violin, another common example of a stringed instrument, okay, various strings, okay, same length, different thicknesses, different tensions, okay, and we'll talk more about that later. Okay, the banjo, maybe not so common here, but in southern states. Oh, Susanna, it more common stringed instrument. Okay, and the piano, I think, you know, while the strings are hidden in a typical piano, most people would realize that it is also an example of a stringed instrument. And if you've ever wondered what is the reason for the shape of the grand piano, well, that classic shape allows you to have strings of various lengths. So unlike the guitar or the violin, okay, the piano can have strings of different length and different thicknesses and different tensions, and when the keys are struck, the strings are plucked and you get notes of various frequencies. So when it comes to the standing waves that get formed on these strings that produce the notes that we hear, all of these above instruments represent strings of, we'll say, length L that are fixed at both ends. And when the string gets disturbed somehow, either by being plucked, bowed, in the case of a violin, or struck, as in the case of a piano, waves of various frequencies, okay, are created which travel down the string. Now, recall in our discussion of wave theory that when that wave travels down a string and reaches the end, okay, you will have a reflected wave, okay, it will be reflected from the end and travel back in the opposite direction. So basically, these incident waves that are traveling down the string are interfering with the reflected waves that are traveling in the opposite direction. Now, for most frequencies, those the frequencies of the waves that are sent down will randomly interfere with the waves that are reflected from the end, and they will die off. Okay, for most frequencies, you will get, you know, partial destructive interference, so that the amplitude of those waves will not be significant. Okay, and they will quickly disappear, not creating much sound. But Okay, for wave frequencies that correspond to the standing wave frequencies, these are what we call the harmonics. Standing waves are created which persist and don't die off, and these end up being the sounds that we hear, okay, that we call music. We will see in some of the upcoming slides that by imposing boundary conditions, okay, on these strings, the imposition of these boundary conditions leads to the quantization of frequencies and allows us to predict, okay, what sort of standing wave frequencies will get created, what sort of notes we can get with these various stringed instruments. All right, so what are the wavelengths of the standing waves that end up getting formed on these stringed instruments? These are what we call the resonant wavelengths. So you recall in our study of standing waves that the standing wave function takes on this form, okay, 2a sine kx. Remember that represents, okay, really the amplitude of the standing wave times this cos omega t factor. So that is the form of the standing wave. Now, okay, if when we impose the boundary conditions, okay, remember we said the ends of the string have to be fixed, okay, and since the ends of the string are fixed, that means that where they are fixed, the strings have no displacement there. They are not allowed to move. So their displacement from equilibrium is 0 for all values of t. This is what we mean by imposing a boundary condition. So we require that the displacement, okay, at the ends, that is when x has a position of 0, that would represent one end, and when x has a value of L, that would be the other fixed end. For all values of t, but for those two positions, okay, the displacement of the string is 0. Well, if we start with the x equals 0 end, okay, when we plug 0 in for x to our standing wave function, we see that, okay, 2a times the sine of 0 cos omega t is 0. Well, this is going to be true for all values of time, okay, that when x is 0, okay, it doesn't matter what time we're talking about, okay, that this boundary condition is true, that the displacement, okay, at x equals 0 will be 0 regardless of the time you look at. But let's take a look at what happens at the other end of the string. So when x has a value of L, okay, this is the other end of the string which is fixed, and we plug in the value, okay, x equals L into our standing wave function, we get the 2a sine kl cos omega t is equal to 0. Now this is true only when, okay, this factor here, sine kl, has a value of 0. We thus require then, remember k is what we call the wave number, and there's going to be more than one possible value for k, so we will use a little subscript n to represent the different possible values. So sine kl will be 0 when kl is equal to a multiple of pi. Right? You know that the sine of pi is 0, the sine of 2 pi, the sine of 3 pi, sine of 4 pi, and so on. So when we say that, okay, k times L is equal to some multiple of pi, okay, some integral multiple of pi, that satisfies the boundary condition. And from here, we want to get an expression in terms of wavelength, not wave numbers. So let's substitute in for k, the definition of k, which is 2 pi over lambda. So we substitute that in and we end up solving for lambda. And we find out that, okay, the wavelengths of the allowed standing waves, okay, those resonant wavelengths we call lambda sub n, will take on the values of 2 times the string length divided by n, where n takes on these natural number values of 1, 2, 3, and so on. So when we talk about the normal modes, or sometimes called the harmonics, okay, what we're talking about is an allowed standing wave pattern. So from our previous slide, we said that the resonant wavelengths, the allowed wavelengths for a string that is held fixed at both ends, okay, must be equal to twice the string length divided by n, where n takes on these natural number values of 1, 2, and 3, and so forth. So we can solve this for L, and we find out that the length of the string, okay, will be an integral multiple of half wavelengths, okay, lambda n over 2. So this tells us something about what these standing wave patterns will look like on our string, and we'll talk about it in more detail in the next slide. But here I'll show you some examples of standing waves formed on strings. Now, normally we don't see this. We don't see these standing waves because they're traveling fast, and your eye is not capable of discerning them. But if we use some stroboscopic photography, okay, so you're only looking at these standing wave patterns at certain times, okay, you can see, okay, that you clearly do get, okay, these standing waves that exist on these strings that are fixed at both ends. So in this slide, we'll describe these normal modes, starting with the lowest frequency normal mode or resonant standing wavelength that exists. So it turns out that there's actually two different naming systems. I have no idea why, but you need to be familiar with both of them, that describe the frequencies of these standing waves that get created on the strings. So in one naming system, we call the lowest frequency standing wavelength the fundamental mode, okay, or fundamental frequency, and then each higher frequency after that we call the first overtone, second overtone, third overtone. In the other naming system, the lowest frequency standing wave that can get created on the string is what we call the first harmonic, okay, the next lowest, the second harmonic, third harmonic, and so on. So two different naming systems. And when we look at the, we said that these standing wave patterns, okay, we can write in terms of lambda, okay, the wavelengths, or we can write in terms of the string length here. Either way, okay, the lowest frequency standing wave corresponds to a value of n equals 1. So if we want to describe this in terms of the string length, we can say where that is the length of the string is equal to 1 lambda over 2, or half of a wavelength. So this is what the standing wave would look like. And you'll notice here that since we have a string that is fixed at both ends, the ends themselves, where there's no displacement of the medium, must be nodes. So here, okay, and here we have nodes, and in between we're going to have an antinode. So that is the lowest frequency standing wave available for a string fixed at both ends. Is where the ends are nodes. That must happen, right? Because they are physically fixed there, and there's an antinode in between. If we look at the next highest frequency standing wave, either the first overtone in one naming system or the second harmonic, this corresponds to a value of n equals 2, okay, or when the string has a length of 2 lambda over 2, or 1 wavelength. So this normal mode, this resonant wavelength, okay, this standing wave pattern looks like this. And you'll clearly see here that we have to have nodes at the ends because the string is fixed, but now we have a node in the middle. Okay, and of course in between any two nodes we have an antinode. And if you look at this, this corresponds to 1 wavelength. Okay, so this is the next highest frequency standing wave. Moving on from there, when n has a value of 3, or when the length of our string is equal to 1.5 wavelengths, 3/2 wavelengths, okay, our standing wave pattern will look like this. And if you trace this out, okay, this looks like 1.5 wavelengths. Notice that we still have the nodes at the end, at the ends of the string, but now we have two nodes in the middle, okay, with antinodes in between. So we see here that this vibrating string is in segments of half wavelengths, right? So in the fundamental frequency, the first harmonic, this corresponds to 1.5 wavelengths. Okay, the next one to 2 halves or 1 wavelength. The next highest frequency, okay, 3 halves or 1.5 wavelengths. And the last one we'll take a look at is when n has a value of 4. That is our third overtone or fourth harmonic. That corresponds to a string length of 2 wavelengths, okay, where we have a standing wave pattern that looks like this, okay. As always, the ends are nodes, but now we have, 1, 2, 3 nodes in between, okay, our nodes at the end, or we have, in terms of half wavelengths, 4 segments of the string, okay, that are vibrating in half wavelengths. So now that we've talked about what our standing wave patterns look like, okay, in this slide we'll talk about what are the corresponding frequencies, okay, to these various normal modes, these various standing waves that are formed on the string. So to derive an expression for the resonant frequencies, we'll start with the wave equation that we are very familiar with, that the wave speed goes like the wavelength times the frequency. Now, if we talk about waves traveling down a string, then we've derived this expression here. We know that the speed of the wave on a string goes like the square root of the string tension divided by the linear string density. That is the mass per unit length of string. So using that and in conjunction with the wave equation, we can derive this expression for the resonant frequencies. Right? The resonant frequencies will be equal to the wave speed divided by these resonant wavelengths, lambda sub n, that we talked about in the previous slide. So here we have our expression for the resonant wavelengths, okay, these normal modes. And when we make the substitutions here, the resonant frequency v, okay, wave speed divided by lambda sub n, okay, we'll write it as v times n divided by 2l. And we will now make the substitution for v, okay, specifically for the speed of a wave traveling down a string, okay, that has tension in it. So here we have it, okay, here we have an expression for the various resonant frequencies. So of course n takes on these integer values. So our lowest frequency standing wave would correspond to the case where n equals 1. Okay, 1 over 2L times the square root of the string tension divided by the mass per unit length, and we can work our way up from there, okay, to determine each of the frequencies of, okay, the higher harmonics or overtones. So from this expression for the resonant frequencies that we derived on the previous slide, we can see how notes of different pitch, different frequencies are produced for a stringed instrument. So different ways to produce these different notes. Let's take a look. First of all, we see the dependence on string length, right? There's an inverse relationship between the length of the string and the frequency of the standing wave produced. So that inverse relationship tells us that as the string length increases, the pitch decreases. So clearly you can see, and we talked about this in a previous slide, that a piano has strings of different lengths, okay, in order to produce notes of different pitch, okay, of different frequencies. Now, while the strings have the same length, note that with the guitar, the fingering of the guitar changes the length of the string, okay, in order to produce different frequencies. Also notice here the dependence on string tension, okay, that there is a direct relationship between string tension and frequency. So as the tension increases, the pitch increases. Certainly guitar, pianos, their strings are tuned by changing the tension in the strings. So of course not all the strings on a stringed instrument will have the same string tension. Okay, we'll look at an example of that in the next slide as well. The third way to produce different frequencies, okay, on a stringed instrument, okay, notes of different pitch, would be by changing the string density. Notice that there's this inverse relationship here between the string density and the frequency. So as the string density increases, the pitch decreases. And you'll notice that pianos and guitars have strings of different thicknesses. Some strings, which appear very thick, almost look like little springs more than they do strings. And so by having those thicker strings, those are the ones that give you the lower pitch notes on the guitar or the piano. And in the next slide, we'll take a look at some examples of that as well. So how do you produce notes of different pitch, different frequency with a stringed instrument? There's really three ways this is done with real musical instruments. So one of the ways is by actually changing the length of the string. Now obviously with a piano, for example, you'll notice the shape of a grand piano has that characteristic shape because it's got, each of those keys has a different length string. With a guitar, the strings are the same length, but the string can be fingered to shorten or lengthen it. So basically that's what we're going to do here. We have a string here which rather than fingering, I can put this this little wedge here to change the length. Let's see what happens here. I'm going to start with a long string and we will gradually shorten the string length. Okay, and remember what we talked about previously, the relationship between the amount of vibrating material and the frequency. You'll see illustrated here. So for a long string, okay, notice how low the pitch, how low the frequency of the standing wave setup is. Let's shorten the string here, and you should be able to, okay, hear the pitch increase. Shorter yet. And let's get a shorter string. Okay, so you see here that as the length of the string decreases, okay, the pitch of the sound increases, that inverse relationship between length and pitch. So a second way of producing notes of different pitch with a stringed instrument is by changing the string tension. And this is how stringed instruments are actually tuned, okay, typically by changing the tension. So you'll notice here what we have, we're going to focus on this one string here, and there's a certain weight on the end of the string that produces a certain amount of string tension. Right now we have not a lot of weight, we have a low string tension. Listen to the pitch of the sound produced when I pluck the string. Notice a pretty low pitch. Let's start adding weight to it, and let's take a look at what happens to the pitch. Okay, adding more weight, increasing the string tension. So you see there that direct relationship between the tension of the string and the frequency or the pitch of the sounds produced. So a third way that notes of different pitch, different frequencies can be produced on a stringed instrument is by the string thickness itself. And you'll notice that, for example, with a guitar, not all the strings have the same thickness. Same thing can be said about pianos as well. So let's take a look here. I have two strings. You'll notice that this string over here is quite thin in comparison to this string, which is much thicker. Both strings have the same length, and both strings are under exactly the same string tension. So the only difference between these two strings,
okay, is there differing thicknesses. Let's take a look at what happens when we pluck each of these strings. And remember, use what we said in a previous lecture about the amount of vibrating material. So we would expect a thicker string, we get more material vibrating, should produce notes of lower frequency than a thinner string. Let's see if that is indeed the case. Okay, so those standing waves produce a fairly low frequency sound. Okay, clearly there you see a higher frequency sound, okay, produced with the thinner string. So it looks like there's an inverse relationship between string thickness and the frequency of the standing waves produced.
So now that we've seen how notes of different frequency, okay, notes of different pitch are created on stringed instruments, in the remainder of today's lesson, we'll turn our attention to wind instruments to see how standing waves, okay, and notes of different frequency are created in columns of air. And we'll start by taking a look at this demonstration of the singing pipe.
Have you ever heard a pipe sing? Well, you're going to get to today. You're in for a real treat. We're going to make this pipe sing for you. Just want to point out here, this is no ordinary pipe. If you look inside the bottom of this pipe, you will see a wire screen, okay, which we are going to heat up and eventually get this to sing. So it's going to take me a little bit of time to heat this up. So what we're going to be talking about today is standing waves that get set up in columns of air, okay, like this pipe here, which is an example of an open tubed instrument. We can get the air vibrating inside of there, and we'll get standing waves set up, which will produce noticeable sounds here. Okay, I'm going to pour out the sound here. And so by the end of today's lecture, I'm going to pour out the sound here. By the end of today's lecture, okay, you'll be able to explain where the notes come from, okay, in vibrating columns of air, like this pipe.
All right, so what's happening in this demonstration to cause the sound you hear within that pipe? Well, notice that we had a flame at one end, and that flame heats the special stainless steel screen which has been inserted into one end of the metal tube. This glowing hot screen heats the air inside of the tube, causing the hot air to rise and cool air to enter the bottom end. So, in a sense, creating airflow in the pipe. Because the air passes through the many holes in the screen, a turbulent flow pattern of air fills the tube. Okay, the noise is produced because certain frequencies of sound from the turbulent flow of heated air resonate within the tube cavity. This is similar to the operation of an organ pipe. The longer the tube, the lower the resonant frequency. And we'll see this in some of the upcoming slides to see how different frequencies, different pitches are created in these tubes of varying length. So can I really pour all the sound out of the pipe? Definitely not. When the tube is horizontal, the airflow pattern is disrupted and air no longer flows through the pipe, thus causing the sound to cease. Right, so just as in the case of stringed instruments, let's start our discussion by looking at some common examples of wind instruments. And when I say a wind instrument, basically, we have an instrument that allows for a resonating column of air. Certainly the flute, a common example of a wind instrument. The trumpet, another example of a wind instrument, that makes different notes, different sounds by getting a column of air to resonate. The recorder, couldn't find an image of that, but a commonly played instrument in elementary school. Maybe some of you played the recorder. The saxophone, Okay, there is one of our former presidents, okay, Bill Clinton, who was a saxophonist. Okay, would very often play on some of the late night talk shows. Okay, what about the trombone? Okay, there's Donald Duck playing the trombone. Okay, another example of a wind instrument that gets different notes by getting a column of air to, okay, vibrate at certain frequencies. The oboe, okay, which apparently looks like that. Okay, and the pipe organ, we talked a little bit about that. Okay, there's our famous, everybody's famous Great Dane, Scooby-Doo, playing the pipe organ. Now, unlike in the case of stringed instruments, where stringed instruments all make use of the fact that you have a string that is fixed on both ends, okay, forcing nodes at the ends of the string, when it comes to wind instruments, we really have two classes of instruments. We have what we call, okay, an open tube instrument where the ends of the tube or the pipe are open at both ends. And then we have a class that we call a closed tube instrument where not both ends are closed, but one of the ends of that tube is closed. Okay, the other end remains open. All right, so how do you get standing waves formed in a tube of fixed length in a column of air? Well, it turns out that there is some sort of vibrating object at the open end of the tube, and this vibrating object creates longitudinal sound waves which will travel down the tube. And just as we said in the case of a stringed instrument where we have a string that is fixed at both ends, we said that the incident waves that are traveling down the string will interfere with the waves that are reflected from the end of the string. And of course, for certain frequencies, you will get standing waves produced. The same thing happens here, okay, that when that vibrating object sends a longitudinal wave down the tube, okay, that when that wave reaches the end of the tube, some of that wave energy will get reflected at that boundary between the media and create a reflected wave that will travel back in the opposite direction and will interfere with the incident wave. And just as in the case for strings, for certain frequencies, okay, a standing wave will be produced. Now, I think it's pretty clear if you have a closed tube instrument, when that wave gets to the end of the tube, there's going to be a reflected wave because there's a clear definitive boundary. But how do you get a reflected wave in the case of an open tubed instrument? And here we can say that the wave reflection at the open end of a tube occurs, okay, because the character of the medium changes even if the material of the medium does not change. So remember in our discussion of wave theory, we said that whenever the medium changes for whatever reason, this causes a change in wave speed, and this is going to cause, okay, some of the energy to get reflected at that boundary, okay, creating a reflected wave traveling in the opposite direction. We'll now turn our attention to the normal modes, that is the allowed standing wave patterns that can form in a tube open at both ends or a tube that is closed at one end. To understand the allowed standing wave patterns, we need to start by identifying the set of boundary conditions that lead to standing wave formation. So starting with the closed tube, okay, remember we said that a vibrating object at the open end of the tube sends a longitudinal sound wave, okay, down the tube, and when that sound wave reaches the end of the tube, okay, which is closed, we can see that the molecules are not free to move there. So in terms of a pressure wave, a sound wave, this would correspond to a displacement node. Okay, a node because just as in the case of a wave on a string that is fixed at an end, at the end where a string is fixed, the molecules of the medium are not allowed to move. So that is what we call a fixed node. It is a boundary condition. For the case of a longitudinal wave, we have the same thing. If the tube is closed, we are physically restricting the molecules from moving there. That corresponds to a displacement node. And remember, in our discussion of sound waves, of longitudinal waves, we said that there is a 90-degree phase difference between, the molecular motion, the displacement model for the wave, and the pressure model. So where we have a displacement node, where those molecules are not free to move, that is going to be a pressure antinode. That means that the pressure there will be high, will be a maximum. Now in the case of the open-tubed instrument, when the molecules traveling from the end with the vibrating object to the open end of the tube, there we see that the molecules are free to move when they reach that end which is open. That corresponds to a displacement antinode, and there, we would infer that that would be a pressure node because, the pressure there would be a minimum since the molecules are very free to move there, are not restricted in any way. So keeping in mind what we just said on the previous slide, in this slide we'll see how these boundary conditions on both the open tube and closed tube will lead to the normal modes, that is, the allowed standing wave patterns. So, to start off here, the wavelengths of the standing waves, that is the resonant wavelengths, if we start with the open-tubed instrument, remember we said that where the tube is open, that must correspond to a displacement antinode. That is a boundary condition on the end of the tube. And since our tube is open at both ends, then this would imply that we must have antinodes at both ends of that tube. Now, if you look at the lowest frequency allowed standing wave pattern that would correspond to having antinodes at the end of the tube, there must be one node in between that. In which case, we can see that the lowest frequency allowed standing wave pattern would correspond to the case where the length of the tube was equal to 1/2 of a wavelength and you had antinodes at both ends. Now to put this in writing here, we can say the forced antinode condition implies that the tube length L must be an integral multiple of half wavelengths. In other words, L must be equal to n, where n is an integer, times lambda over 2. So like we said, I'm showing you in this picture here the lowest frequency case where we have two antinodes at the end, one node in the middle. That would be the case where n is equal to 1 and the tube length is half a wavelength. Of course, the next highest case would be where n has a value of 2. The length of the tube would be equal to 1 wavelength. And we'll take a look at that picture on the next slide. So when it comes to a closed tube instrument, when we take a look at the boundary conditions, remember we said that where a tube is closed at one end, that must correspond to a displacement node. So here, when I look at my tube here, we must have an antinode at the open end of the tube. I'm showing you here. But at the closed end of the tube, that must correspond to a displacement node. Notice in this case here that the length of the tube, where we have an antinode at the open end and a node at the closed end, that length of that tube corresponds to 1/4 of an entire wavelength. So here, putting this in writing, we can say the forced node-antinode condition implies that the tube length L must be an odd integral multiple of quarter wavelengths. We can say that L must be equal to n lambda over 4, where n takes on these odd integral values. And we'll see some of these higher frequency standing waves in the closed tube on the next slide. So let's take a look at these normal modes, these harmonics, starting with the open-tubed instrument. and we'll look at some of these allowed standing wave patterns, starting with the lowest frequency. Okay, that is the fundamental mode, or the first harmonic. So remember, we said this corresponds to a value of n equals 1, where we said that the length of the tube, this is from the previous slide, has to be an integral multiple of half wavelengths. So the lowest frequency standing wave that we could get would be where we have the two antinodes at the end of the tube, okay, with a single node in the middle. That corresponds to 1/2 of a wavelength. The second harmonic, or first overtone, would correspond to a value of n equals 2, okay, where the length of the tube is equal to 2 lambda over 2, or a 1 wavelength. Again, we must have antinodes at the end of the tube, but in this case here, we have 2 nodes in between, okay, rather than just 1. This corresponds to the case where the length of the tube is equal to 1 whole wavelength. And the third harmonic, or second overtone, corresponding to the case of n equals 3, would be where the tube length is equal to 1.5 wavelengths. Okay, once again, the ends of the tube, because they're open, must correspond to displacement antinodes, but in this case, we would have 3 nodes in between. In this slide, we will do exactly what we did in the previous slide, but this time for the closed tube wind instrument. That is a pipe with one end that is closed. So what are these allowed standing wave patterns? That is what we call the normal modes for the closed end pipe. Starting with our lowest frequency standing wave, okay, what we call the first harmonic, or fundamental frequency, where n has a value of 1, we impose these boundary conditions to determine the allowed standing wavelength. So for the end of the tube that is closed, the molecules of air are not free to move there, in which case we must have a displacement node. Okay, there's got to be a displacement node at the end that is closed. But for the open end of that instrument, for the open end of the pipe, okay, this must correspond to a displacement antinode, okay, just like we talked about for the case of the pipe that was open at both ends. Why? Well, as we said, the molecules at the open end are very free to move there. So we would expect an antinode there. When we look at the lowest frequency or longest wavelength standing wave that meets this criteria, where we have a node at the closed end and an antinode at the opened end, okay, we see that this corresponds to the case where the length of our tube is 1/4 of a wavelength. So we can work our way up. The next highest frequency standing wave, and this may sound a little strange here, but it's not n equals 2. As we will see, n equals 2 does not meet our boundary conditions. So the next normal mode would be what we call the third harmonic, or first overtone. This corresponds to an n value of 3. Okay, and when we draw this picture, the next lowest frequency, longest wavelength standing wave, we must have a node at the closed end and an antinode at the opened end, but now 1 node in between. So this is what the normal mode, this is what the standing wave pattern is going to look like. This is where the length of the tube corresponds to 3/4 of a wavelength. So you see here that our traditional case where n equals 2 would not meet these boundary conditions. We have no even number harmonics for the pipe that is closed at one end. And we'll take a look at one more normal mode. Okay, the next highest frequency standing wave, or maybe I should say lowest frequency standing wave, would correspond to an n value of 5. Okay, in which case we will add one more node, but we will keep this criteria that the closed end must be a node and the open end must be an antinode, in which case we have 2 nodes in between. This corresponds to the case of 1 1/4 or 5/4 wavelengths. So from the resonant wavelengths on the previous slide come the resonant frequencies that we'll derive on this slide. So of course we have both open tube and closed tube instruments, so we really have two conditions to be able to arrive at the resonant frequencies depending on what type of wind instrument you've got. So starting with the open tube instruments, and just like we did for the case of stringed instruments, we'll use our wave equation, V equals lambda times F. And from our previous slide, remember the resonant wavelengths for the open tube are those where we take twice the tube length divided by N. Okay, enter these natural number values here. And from our wave equation, the resonant frequencies are just the wave speed divided by these resonant wavelengths, which we plug that in, gives us V times N over 2L. Note here that this is exactly the same equation as for the stringed instruments, right? Okay, this condition determining the resonant frequencies looks identical. The only difference is that here, V, the speed is really the speed of sound in air as opposed to the speed of a wave on a string. But the frequency condition looks similar. When we turn our attention to the closed tube instruments, once again using the wave equation and making the substitution, remember here the resonant wavelengths are given by this condition 4 times the tube length divided by N, where N takes on these odd integer numbers. Substituting that in, we find out that these resonant frequencies are given by wave speed times, our odd integer N divided by 4L. So there we have it. These are the the equations that determine the resonant frequencies for the allowed standing waves you can get in both an open tube and a closed tube instrument. And lastly, we'll see how, given this formula we have for the resonant frequencies in both open tube and closed tube instruments, this is the open tube instrument I'm showing you here, how are notes of different pitch actually accomplished with these instruments? In this slide we'll take a look at how that's done, and we'll look at some examples that will take place in the following slides. So the first method to be able to produce different frequency notes in these instruments is by changing the wavelength, really changing the length of the air column. And if you look at this equation, and I realize that this is for the open tube instrument, but we have a similar expression for the closed tube instruments, we see that there's this inverse relationship between frequency and tube length. So clearly here we see that the longer tubes correspond to the lower frequency notes. And when you take a look at the pipe organ, we mentioned this previously, your longer pipes are the ones that produce the lower pitch notes. We'll take a look in the next slide to see this relationship in action in an example of an instrument that even somebody like myself who completely lacks musical talent, here's an instrument that even I can play. We call it the soda straw oboe. Another way to change the frequency of the sounds in an instrument is by changing the frequency of the vibrating source itself. And we will take a look at doing this in the case of the flaming pipe. A third way would be changing the wave speed. And to do this, you would actually have to change the medium itself. So an example of this, again, another instrument that even I can play is what we call the bluegill. We'll take a look at that in the next slide. But clearly you can see here that there is a direct relationship between the frequency of the wave and the speed of the wave in that air column. So changing the wave speed is another way to do that. Is kind of an interesting example here. I asked, when helium from a helium balloon replaces the air in your throat, you can talk in a cartoonish high-pitched voice, and I'm sure that many of you have done this. If you do this, you end up kind of sounding like Donald Duck. What's going on? okay, to do that? Well, as you can see here, okay, you're changing the speed of the wave, okay, in the column of air that is your throat. The typical speed of sound in helium is quite fast, about 972 meters per second, whereas you know that the speed of sound in air is only about a third of that, 343 meters per second. And since that frequency is directly proportional to wave speed, an increase in wave speed should correspond to an increase in frequency. So by replacing the air in your throat with helium, where the speed of the wave gets about 3 times faster, the frequencies of the sounds that are produced, okay, in your throat, okay, by your vibrating vocal cords will be much higher. So in the next slide, let's take a look at some of these examples, okay, in action.
So one of the ways to produce notes of different pitch, notes of different frequency, okay, in a vibrating column of air is by changing the length of the air column. So classic example of this, think about the pipe organ. You'll notice that all those different pipes, okay, have different lengths to produce, okay, different standing wavelengths of different frequencies and pitch. So here's another instrument that even I can play. And this is what I call the soda straw oboe. You'll notice on one end I've cut it to make it look like a reed. And right now the straw has a certain length. Okay, but take a look at what happens when we shorten the length of the tube. Okay, take a listen to the changing pitch of the sounds created. So here goes. I'm going to try to get the vibrations to happen. I'm going to shorten the length of the tube. Listen to the frequency. Soda straw oboe, folks. Gotta love it.
$272. $292. $313. $335. $355. 376, 399, 419, 440, 461, 470, 483, 505, 514.5, 526, 557, 597, 643, 682, 723, 763, 771, 812, 857, 903, 948, 991, 1037, 1075, 1120, 1159, 1205, 1246, 1291, 1,329, 1,373.
So I finally found an instrument that even I can play. This is what we call the bluegill. It is a corrugated pipe, okay, and similar to the bugle, which can only produce a few notes, 3 I believe. Okay, this corrugated pipe is capable of producing 3 notes as well. And one of the ways that you can produce different pitches, okay, get different frequency standing waves set up in a wind instrument is, okay, by having the air travel through that corrugated pipe at different speeds. So here, I'm going to hold one end of the bluegill fairly stationary. The other end is going to twirl through the air. And so you see that the end of the pipe that twirls through the air, okay, the airspeed at that end will be greater, okay, than the relatively stationary end. And according to Bernoulli's principle, that's going to cause a pressure gradient, okay, across the ends of the pipe, which is going to cause air to flow up through it. And when the air passes those corrugations, okay, at a given speed, it will cause the air in those corrugations to start vibrating, okay, at a certain frequency. So here, the faster I can spin this corrugated pipe, okay, the greater the pressure differential across the ends, the greater the air speed, okay, and the higher the frequency of the note produced. So let's see if we can do this. I'm going to start out spinning it slowly with a low frequency, and I will gradually increase the speed. So here's the lowest frequency note. Let me spin it a little faster here. We'll get the next frequency note. Okay, and we'll see if we can produce the highest frequency note by spinning it even faster. The bluegill, folks, an instrument even your physics professor can play.